Hi, everyone. Welcome to the colloquium. It's my pleasure to introduce our speaker, Bento Natura, who comes from Columbia University, where he's an assistant professor in industrial engineering and operations research. He spent 2 years as a postdoc at Georgia Tech, Brown University, and UC Berkeley, and obtained a PhD in mathematics from the London School of Economics. His research interests are focused on the areas of algorithms, optimization, and game theory, with a special emphasis on the theory of linear programming, which explains the talk today. So please take it away.
Thank you very much, Sam, and thanks for inviting me. It's a pleasure to speak here in this Tutte Colloquium. So what I'm going to talk about is research that essentially spanned a few years of us that I would say not culminated, but as a nice intermediate step has this result here, that we can now solve LPs with 2 non-zero entries per column or row in strongly polynomial time. And that's joint work with Daniel, with Cedric, who did his master's here, bachelor and master, with Neil, and with Lazi. Okay, so what are we looking at? We look at LP in their standard form. So we have equality form, we have non-negativity of our variables, and we want to minimize a linear objective. And for 50 years now, so we have methods that do that in polynomial time, meaning that we can solve them exactly in a running time that is polynomial in the number of variables and in the bit size, in the bit encoding of your input. So in the bits of A, B, and C, which is the data of your problem. So there are two big classes of problems that do it. First, the ellipsoid method by Kacchian, and then Kamarka a few years later with the tier point methods. However, what is still open, and is a big open question in the area, is can we turn polynomial into strongly polynomial, which would mean can we drop the dependency of the running time on the bit encoding size of A, B, and C. So just as an example, if you would want to solve a linear system, then you do Gaussian elimination, and if you're a bit careful, then this runs in strongly polynomial time. The number of steps you need to do it is polynomial in the number of variables that you have. So the question is, does a similar algorithm exist for LP? And there are quite a few classes for which we can do it. Let me mention that there is a second requirement except for the number of steps that you require to be polynomial in M. You need also to stay in polynomial space. However, this is usually something that you can achieve, at least for LP. And what we've done now is that, okay, we found an algorithm that at least if we have the structure that we have at most 2 non-zero entries per row or per column, then our algorithm runs in strongly polynomial time. Okay, so this captures things like bipartite matching, like minimum cost flow. Of course, for these problems, we knew already a strongly polynomial time algorithm, but this is essentially a generalization of that. Okay, and as a side note, there's a simple reduction of general LP to LP with at most 3 non-zero entries per row or column. In particular, sort of if you want to parameterize complexity by the number of non-zeros per row or column, then 2 is the most you can get before solving the whole problem that is here in red. And one thing I should maybe mention about the computational model is that we work in real RAM. So the question is, what does it mean to not have dependency on the size of your numbers? If you would work with bits, then your operations would be in bits, so of course you would have dependency. It is more like you have an oracle that can add, multiply numbers, can compare numbers, and these are the operations that you allow. Okay. Now the general problem for 2 non-zero entries per row or column is that you can have either positive or negative entries, and Henry just asked me before the talk whether I do make this restriction to certain signs. It turns out that Dürr-Hochbaum in 2004 has a very simple reduction of the general problem of 2 non-zeros with any sign to 2 non-zeros where 1 is positive and 1 is negative, which then is called the minimum cost generalized flow problem, which is, as the name says, a generalization of the minimum cost flow problem. Namely, if you think of the gammas here that you see, which are non-negative numbers, as all 1, so think of gamma as the all 1s vector, then this is exactly minimum cost flow. So what are we trying to do? We try to minimize the cost of a flow x such that the flow routes exactly the demands B around our network. Okay. And in generalized flow, it is the case that you have these gamma factors, which corresponds to, if I send 1 unit out over an arc, then you send 1 unit out of the tail, and gamma many units arrive at the head. Okay? So from now on, I will, in this talk, consider this problem here, minimum cost generalized flow, where essentially you think of working on a graph. So essentially this whole problem of optimizing over an arbitrary constraint matrix is now reduced to optimizing over a network with generalized gains. So the gammas are so-called gains, and that's what we're going to look at from now on. Okay. So what has been known for this problem before our result? Let's start with special gain factors. As mentioned, gamma, all 1, corresponds to the minimum cost flow problem, and that has first been shown to be strongly polynomial by Eva Tadosh in 1985. In fact, even other gain factors gamma give you, since the mid-80s, strongly polynomial time algorithms. 1 year later, Eva Tadosh had a paper that said you can solve LP in strongly polynomial time whenever your matrix is integral and the integers are at most exponential. So in particular, that means for our problem, if the gammas are integral, if their logarithm is a most polynomial, then you can solve it in strongly polynomial time. So that leaves us only the case where gamma is really nasty in a way, to where we don't know how to solve it in strongly polynomial time. If you think about now general gain factors gamma can be irrational, and we care about primal feasibility, which means forget about the cost vector C, I just want to route with a negative flow the exact demands around our network. This is for minimum cost flow is trivial, like this is a linear time algorithm. But here, of course, it's highly non-trivial if you have these gain factors gamma. And it took a very long time, until 2013, to find a strongly polynomial time algorithm that has since been simplified in 2020 by Lazzi and by Neal to an algorithm that is quite competitive in theory, at least, m squared n. If you compare that to what we know for min cost flow, which would be mn, then it's not too much worse. So this is primary feasibility. Dual feasibility, which would correspond to, I have not written down the dual here, but the dual is exactly the following problem. You have a bunch of inequalities, and in every inequality there are 2 variables appearing, or at most 2. So this is dual feasibility, and it turns out we have algorithms for that for much longer. Megiddo in the mid-80s came up with the first algorithm. In fact, he introduced the technique of parametric search in that paper, which is, yeah, as mentioned here, it's a bit like binary search, but a lot smarter. It's a bit of a meta algorithm as well. So yeah, let me not get into details here. The fastest algorithm that does it deterministically is Hochbaum and Sefi-Naor, order m squared. And let me mention one algorithm that is a bit different in flavor, because both of these algorithms use the new technique of parametric search. Our algorithm is more combinatorial, and the first algorithm that you could qualify as combinatorial that solves the problem. And it's essentially, it's a discrete Newton method. And I also spoke actually with Henry here about this sort of method, where at the end of the day, it boils down to finding a root of a one-dimensional convex function. And it turns out that this algorithm runs in strongly polynomial time. Yeah, so that was the state of the art until 2021. We have primal feasibility algorithms, we have dual feasibility algorithms. In general, you would think that optimization should not be too hard. In particular, if you don't care about strong polynomiality, these 2 things are usually good enough for you to be able to optimize. But yeah, if you think a bit about it, then it's clear that it's highly non-trivial how optimization would follow in a strongly polynomial world for that. Okay, so how did we approach the problem? We started from a primal side with the results by Neal and Lazzi. There was, since 2017, a very clean primal feasibility algorithm. Then we did ask the question, okay, is there something nice for the dual side? Because back in 2019, we didn't have this discrete Newton method. So all the algorithms for dual feasibility would be parametric search would be, yeah, sort of, again, binary search made smarter, so it's not very combinatorial. And then we figured out, okay, that can be done. There is a strongly polynomial time dual feasibility algorithm. And then what often you do and come up, okay, is there some primal dual framework where you make always progress either on the primal side or on the dual side to solve the optimization problem. And we went off and looked into this problem. And in a completely different thread that had nothing to do with that project, on the left side, we asked, yeah, a more continuous optimization problem here. And that is, IPM here stands for interior point methods. They are, as we've seen on the first slide, are one of the algorithms classes that can solve LP in weakly polynomial time. However, they only give you an approximate solution. They don't give you an exact solution. So our question was, okay, if we don't care about weakly polynomial, we just want that it solves the problem exactly in some running time in the dimension, can we design such an interior point method? So that is the question here. And on the left-hand side, on this project on the left, we didn't make any progress in a couple of years. I had no idea how to do it. So let me speak a bit about the one on the right. And I will not speak much about interior point methods here, but just to give a little bit of a gist of what's going on there. So what you need for interior point methods to run is you need some point in the strict interior, preferably very central in your polytope. So we assume that our polytope is strictly feasible. With some auxiliary tricks, you can make it strictly feasible. And what you do is you define sort of an objective function that pushes you away from the boundary. And you design a sequence of strictly convex problems for which you first penalize very hard being close to the boundary, and then you penalize it less and less and less, and you emphasize more the true objective, which is C. And this trade-off leads to sort of a sequence of solutions, which is here, this path in blue. And it turns out that you can follow this path efficiently, where efficiently means within polynomially many, in fact, root number of constraints many, you can reduce the optimality gap by a factor of 2. Okay? So very efficiently, you can reduce the optimality gap to a very small epsilon here, say. But that, again, doesn't give you an exact solution, only a small epsilon error. And turning these into exact algorithms has actually been pioneered also by faculty here. So Steve had an algorithm in '96 where they had an algorithm that solves, this is an interior point method that solves LP in a running time that is polynomial in the number of constraints and the logarithm of some condition number. However, this condition number can be exponentially large, or it can be doubly exponential for minimum cost generalized flow, so their algorithm wouldn't give the strongly polynomial running time. There were a couple of follow-up works where they improved the running time or improved some other aspect of the interior point method, but none of these sort of led to an algorithm that is, let me say, to an optimal interior point method. All these algorithms would have some dependency on some condition number of your matrix, and this condition number can be arbitrarily large, even for our minimum cost generalized flow problems, so these algorithms don't lead us all the way. But then we designed 2 years ago an algorithm that has running time dependence on a different condition number, which we call straight line complexity, which I'm going to introduce next. The nice thing about this straight line complexity is that it's a purely geometric measure. You don't have to understand anything about interior point methods to understand this measure. So how would it be defined? There are several equivalent ways of defining it. Maybe the straightforward way with formulas would be the following. Here we have our primal formulation of our LP. And now for any variable I, so I here is a variable, I define a function that maps from the non-negative orthant to the non-negative orthant. And what we do is we look here at the sublevel sets of my LP, where I look at all the points in my feasible region that have optimality gap at most G. G, again, is the argument of that function. And among all these points in the sublevel set, I look at the point that maximizes my ith coordinate. Okay? So we maximize the xi coordinate for which we define our xim, subject to being in a sublevel set. So in particular, if you look at the extreme scenarios, if g goes to infinity, then this constraint here is redundant. So you look for the maximum, for the point that maximizes your coordinate in the feasible region. If we set g to 0, then you ask for the maximum value of xi in the optimal facet. And between, everything is a trade-off. Another way of defining this curve would be the following. You look at a two-dimensional subspace. One is the subspace spanned by the normal vector of the facet that is defining I. The other one is the objective direction C. And you project your polytope onto this two-dimensional subspace. And then part of the boundary of that polygon is going to be exactly that curve here. Okay. It has very nice properties. So yeah, it is definitely monotone just by definition. But more than that, it is monotone and concave. It has the property that it is piecewise linear. Piecewise linear can be seen by the definition through the projection. In particular, the number of pieces is bounded by the number of edges of the original polytope, because this type of projection, yeah, every edge of the projection is an edge in the original P, and the same statement holds for vertices. So the number of pieces is bounded by the minimum of the number of vertices, the number of edges of my polytope. Yeah, so these are some nice properties that hold for all polytopes. And it turns, yeah?
It doesn't have to start at 0, right?
It doesn't have to start at 0, yeah, true. Yes. Yeah. Okay. Okay, so this is our curve. And now you can define the straight line complexity with this curve, and that's the following. You scale down your curve by a constant factor. The 2 here is chosen arbitrarily. And now you look into this tube that is spanned by these two blue curves from 0 to infinity. And in this tube, you essentially play the following game. You try to find the green curve here, or some green curve, that is a piecewise linear curve in that tube with as few as possible linear pieces. Okay? This you can do greedily. Start greedily at 0. Probably take this gradient here, go up here until you hit it up here, and keep going. It's pretty hard, if you don't go to a logarithmic scale, to draw a curve in 2 dimensions that has a high number of pieces, where the green curve has a high number of pieces. So yeah, maybe this picture is not too illustrative, but this is indeed the definition of the straight line complexity. So here, for this example, the straight line complexity would be exactly 2. And what we've shown 2 years ago, together with Xavier and Georg, is that under the assumption that you have for an interior point method this point that is close to the center that you need to initialize it, we design an interior point method that solves an LP in strongly polynomial time, or in strongly polynomial many iterations, if and only if we have the property that for all variables, this SLC is bounded by a polynomial. Okay? To be more precise, our algorithm's number of iterations is proportional to the sum of the SLCs of the variables. Okay. So now this is a very core notion to this talk. So if there are any questions at this point, I'm happy to take them. Okay.
And you
yeah.
sort of fix some constant, like half that you use for all the variables?
Yes. So it turns out that if I would choose a different factor than 1/2, let's say I pick some factor y to scale it down, then the SLC would change with the logarithm of y. So you can scale it an exponential amount and still remain up to polynomial, the same number of iterations. Yeah, but this, by the way, is just something in the analysis. The algorithm doesn't have to know about SLC or anything. It's just the central path sort of traces the SLC, and in that sense, it's automatic. Yeah. Okay. Good. Let's maybe look at a very simple example, and that is maximum flow. I've written maximum flow here sort of in the standard form, just to sort of confirm with the notation before. So what do we do? Essentially what this is find a maximum circulation on all vertices that are not source or sink, and want to maximize the flow over in the auxiliary arc that goes from the sink T to the source S. And what do we have to do to analyze the straight line complexity? SLC is fix any edge of my graph. And now we think about, again, what was this projection, or what was the SLC definition, or what was the max central path definition? It was the projection of my polytope onto a two-dimensional subspace. And now my piecewise linear curves correspond to edges in the original graph. And the edges in our polytope here are just cycles in my flow polytope. And now we just have to look at what is happening. What kind of cycles do exist? Let's say we have some network here. We want to send flow from S to T, and we analyze the max central path of our edge E here. And which cycles are interesting? Only cycles are interesting that change the objective value. Because in the end, recall that this here is a function of gap. So to change gap, you need to change the flow that you send over the arc ST. So the arc ST has to be involved in the interesting cycles. Now there are two types of cycles. One type involves the edge E, for which I'm currently analyzing my SLC, and one type of cycle doesn't involve it. So here what we have, we have some cycle in the residual graph that involves edge E, and here it avoids edge E. Okay? And now what is the change in the FEM curve, which is the max central path curve for our flow? Here it is 1, but just because, if you send units around a cycle, cycles here are nice. Everywhere is the value 1 or minus 1. Or here, of course, the flow doesn't change at all because we avoid our edge E, which gives a very nice interpretation, very simple interpretation of our max central path curve. Namely, at first we have gradient 1, then we have gradient 0. We have at most 2 pieces in our max central path curve. SLC is at most 2. So recall, entry point methods have running time proportional to SLC. So here it is, you get polynomial running time because poly times constant. Okay, so it is straightforward. Unfortunately, I can tell you that if you look for minimum cost generalized flow, this curve can have up to exponentially many pieces. So the analysis will not carry over. Okay, and also importantly, SLC is a much stronger thing than analyzing the curve directly. Recall that we analyze a scaling of that curve, so something like this here. Okay, of course, number of pieces, of course, an upper bound for the SLC, but SLC can be much, much smaller, and this is crucial. Okay, now, before we figured out the SLC for minimum cost generalized flow, we first went back to different problems, different combinatorial problems that you can phrase as LPs, and checked whether the SLC for them is small. So which classes did we know run in strongly polynomial time before, say, 2022, before we had our algorithm? Combinatorial LP, so these are the ones that can be defined as the ones that have integral entries and the integers are not too large. And classical problems that you can phrase as such are these here. Multi-commodity flow here means the fractional multi-commodity flow problem. And then we had, as shown before, we had primal feasibility of min-cost gen flow. We had dual feasibility, discounted Markov decision processes that was shown by Yin Yu Ye. And then there are a few different problems where, okay, these are special cases. I don't really want to talk about them. If you have small dimension, you can solve LP in strongly polynomial time. It turns out that all of these problems, except for this one here, for this we don't know how to analyze it, all of these problems actually have strongly polynomial straight line complexity. So this can be shown relatively easily. In particular, sort of, we recovered with our 2022 algorithm essentially all algorithms that, so for 2022 there were different combinatorial algorithms, specialized algorithms that solve certain combinatorial LP in strongly polynomial time. But sort of now there's one unifying algorithm that does it for all of these problems at the same time. Okay? Now what is still out of range for interior point methods would be, okay, there are twisted Clementi cubes. There was a result in 2018 first, then published in 2022 in a journal that any interior point method will have a problem with the instance that they created, for which you need 2 to the dimension many iterations. So this is sort of showing that interior point methods will not lead to strongly polynomial time algorithms. You would need to modify the algorithms to eventually solve the big problem. What else? Markov decision processes, still today unclear. We don't have a strongly polynomial time algorithm, and we do not know whether interior point methods do them in strongly polynomial time. And in 2022, there was the introduced minimum cost generalized flow problem, for which essentially, our paper that I'm presenting today, where we show that not only can you do it in strongly polynomial time, but the algorithm that we had in 2022, the interior point method does it in strongly polynomial time. Okay. Good. So to complete this road picture, we did no progress on trying combinatorial approaches to turn prime and dual feasibility algorithms in some optimization framework. There was a separate framework for which we are just asking here, let's just, instead of approximate solution, find exact solutions in dimension-dependent running time. Turns out, yes, we can do it. The answer here was 2 to the number of edges in general, which is sort of the worst case scenario. So here we wrote IPMs are not worse than simplex, and the title was chosen because you can bound the maximum central path, the number of pieces, or the SLC is again upper bounded by the number of pieces, and the number of pieces is exactly the running time that the shadow simplex method would need. So this is why we chose that name. But it turns out that, again, this is a very crude and bad upper bound. In fact, SLC is the right notion, and it turned out that SLC is in fact polynomial for minimum cost generalized flow. Okay. Right. And sort of to give an illustration of how we proved such bound, we have to go into the combinatorics of minimum cost generalized flow. So what is it about them? What is the property that we can exploit there that wouldn't be exploitable by general LP? Okay. And for this, we go into the circuits. I think Steve was asking yesterday whether I speak about matroids, and in fact, I somewhat do. So what are we looking at? We look at the linear matroid, essentially, that corresponds to the column of your constraint matrix. So what are we looking at? We look at the kernel of our matrix, constraint matrix A, and we look at elements in the kernel that are support minimal. Okay, support minimal, but non-zero. For classical combinatorial problems, let's say, let's start with directed graphs. What would that look like? It's exactly what you would think it is. The circuits are cycles. So what happens, essentially you look at the undirected version of that graph, and then depending on the direction, you have ones and minus ones here on that cycle. Circuits for undirected graphs are a bit more complicated. So again, to give an intuition, what are we trying to achieve? Where do the circuits come from? We look if you look at a graph, then every row of this system of equations corresponds to a vertex. And at every vertex, you sort of sum over the inflow and outflow, and this should be 0. In particular, this is in a support minimal structure given by a cycle, because here, in minus out is exactly 0, and yeah, this holds for all the vertices. To achieve that in an undirected graph is a bit harder, because you would need an even cycle length to be able to erase the flow all around the cycle, alternatingly with 1s and minus 1s. If you don't have an even cycle, then you would need 2 odd cycles and join them by a path, and you would need the 2s here. And yeah, you can check that for every vertex, if you sum over the values and the incident edges, then this is 0. And it turns out that this set is inclusion-wise minimal, except for the empty graph to have this property that, yeah, that all the incident arcs sum up to 0 at every vertex. Okay. And by the way, let me mention that you can generalize that, of course, for general subspaces where a matrix is not an incident matrix of a graph. And then you look at the largest entry that pops up in such a circuit, and it turns out that the running time of Natura pod method is going to be polynomial in the dimension and logarithmic in the largest entry that shows up. So just that as a side note. Problem for minimum cost generalized flow is that this largest entry can be doubly exponential, can be arbitrarily large in the dimension. So this sort of condition number analysis will not give you strongly polynomial running time. You need to do something else. But for that, let us understand what actually the circuits are in generalized flow. So let us recall what we're looking at. We look for, again, a circulation. So in and outflow sum up to 0 at every vertex, where now recall inflow is sort of the scaled version by these gamma factors. Okay? But this should be gamma E instead of I. Okay. This is what you try to achieve. Now, there are sort of 2 types of these circuits where you can achieve that. One type of circuit is where if you have, for a cycle, the product of the gammas on that cycle is exactly 1, then this is just a rescaling of a standard cycle, right? So where I mean by standard cycle would be where gamma is all 1. In particular, there are flow values here that you can choose such that in minus outflow is exactly 0 for every vertex. So this is sort of the boring type of cycle, or boring type of circuit that exists. The more interesting and more generic type of circuit are bicycles, where similarly looking in structure to the circuits that we had for undirected graphs, you would have 2 cycles that are joined by a path. But now here the direction is somewhat important. Namely, for one cycle, you want it to be so-called flow generating, meaning that the product of the gammas is larger than 1. And for the other one, you will want it to be flow absorbing, which means that the product of the gammas is smaller than 1. Now, how are you able to achieve that the net flow at every vertex is 0? Well, you just generate flow over this cycle here, make sure that the net inflow and outflow over all of these vertices is 0, but you generate some excess flow here. Now you send this excess flow over this path to this other circuit or this other cycle and destroy it by sending it around. Okay? And this way you can achieve that there exists a kernel element of the constraint matrix that has support exactly this bicycle. And these are the structures, all the structures that there are for minimum cost generalized flow. Okay. And the very, very high level, rough explanation on why the straight line complexity is going to be small for minimum cost generalized flow is that all over your graph, there are going to be exponentially many of these bicycles. However, there's only a small polynomial number of them that actually matters. Okay? So this is, the very, very high level explanation of why SLC is small. Let me go into a bit more detail by explaining why paths, among the exponential set of paths between two vertices S and T, why among them only a polynomial number is going to matter. Intuitively, when you have it for paths, cycles are sort of stitched together by paths, bicycles are stitched together by paths. The argument will follow. The hardest sort of bottleneck for us to figure out the overall running time was to actually be able to bound the number of paths that actually do matter. And now I can explain what it means to matter. For every arc, you associate three non-negative numbers. There's the gain, the gammas that we've seen already. There are arc capacities that we haven't seen so far. We worked in the uncapacitated version, but you essentially work in the residual graph during your algorithm, so this is where their capacities come in, and we've seen the cost vector C. Okay, so three non-negative numbers per arc. I look for the exponential set of ST paths, and now I have a multi-objective optimization problem, and that is the following. I'm looking for a walk from S to T of length at most n, such that I send flow as efficiently as possible from my source to the sink. Okay, so this is the product of the gammas. So I want this to be maximum. Secondly, I want to be able to send more flow along this path than I would be able to send around any other path. Meaning, I can send flow to T and push flow to T as long as possible until any of the capacities is saturated. So I want the total flow that I can send to T on this path to be maximum. And I want to do that at the minimum cost. So for the amount of flow that I'm able to T, I want to pay the least price for that. Okay, so this is three objectives that clearly don't align well with each other. You could easily think of an exponentially sized Pareto frontier. So certainly there would not be a single path that would achieve all of these things at the same time. So let's maybe relax that to the following notion. I essentially gave it away already, is that, okay, let's think about a collection W of walks, collection of poly size, such that for every walk that exists in my graph, there is a representative in my collection that is better in all three dimensions. Again, that doesn't exist. You could have this exponential Pareto frontier, and then, then this question 2 turns out to be false. But you can relax that even further. We want still ask for a polynomially sized collection. This is important to us because the size of the collection is going to translate immediately to the straight line complexity bound. But now we say we allow them to be up to poly size instead of just n. And furthermore, we allow them to be not strictly dominating, as we did ask here, but they are dominating up to a polynomial factor. Okay? So what I'm now asking for is, okay, can I find a polynomial sized collection of potentially longer walks that have the property that for any walk in my graph, there exists one walk in my collection that dominates it up to a polynomial factor in the gain, in the capacity, and in the cost. Okay? And it turns out that if you relax it this far, then yes, there is a very small collection of quadratic size that has all of these properties. Okay. And to give a very rough idea on how you would prove such a thing is the following. Whenever you have any path, then there is going to be the capacity arc, which is the one that is the one that has the least capacity, which will be the one that will be first saturated. And you have a second arc that is the one that has the maximum cost. So for any unit of flow, you sum up the cost over the arcs and you pick the arc max of the cost, and this is going to be your arc UV. These are going to be two arcs in your graph. By the way, they turn out to be distinct arcs. This is sort of a fact from strict complementarity. But yeah, it's not important that they are distinct. And what you now do is the following. For these two arcs, say this arc comes, the capacity arcs comes before the cost arc, you sort of have the freedom to improve your path by patching up from the head to the tail of this arc here with any path that has sort of the same signature. So what you can do is you replace sort of this middle piece by some generic arc. This generic arc only depends on this arc and on this arc. And this generic patch should have the property that no arc on this patch has smaller capacity than our capacity dominating arc ij, and no arc here should be as expensive as uv. Okay? Importantly, this patch, again, only depends on the arc that comes after it and the arc that comes before it. In particular, there are only order m squared many of these patches. Okay? And you can keep repeating this patching. So one issue is that after you patched, it could be that the red and the yellow arc move to different parts of your graph. And what you can show is that this only happens polynomially many times, that they move to different parts of the graph, and it will turn out nicely. You get the bound that you get a collection of poly size. In fact, the size of the collection is order mn. So again, I did not really give much intuition of why this translates into an SLC bound. I gave intuition of why there's a collection of order mn many paths that only matter. And again, you can turn paths into bicycles and so on. This will give you the order mn bound. We had this result, again, from 2 years ago, that interior point method can be designed to run in strongly polynomial many iterations if SLC is polynomial. So these things combined tell you that, okay, if you give me a point near the central path, then I have an algorithm for you that runs in polynomially many, or in SLC many iterations to solve the LP, in particular for minimum cost flow. There are polynomially or strongly polynomially many iterations. Okay, now there are two things here marked in red, and those are non-trivial things to resolve. How do you initialize is the first question. And the second question is, well, you say these many iterations, but you don't say what the bit complexity is or what the complexity of the numbers is that you generate. So one issue is with interior point methods is what you do is you solve a linear system in every iteration, and sort of the data of the linear system in the next iteration depends on the solution of the previous system. In particular, the bit complexity can, in theory, within logarithmically many iterations explode. Okay, so it's unclear that within poly many iterations you still have small bit complexity, and this takes some non-trivial effort to resolve, but it's really not very interesting. It's sort of clever rounding, but there's nothing interesting happening there. Initialization is sort of a bit different topic. Somewhat, even if you don't care about strongly polynomial algorithms, initialization can be a struggle. And let me sort of talk about initialization methods that, are common in theory and practice that, unfortunately, for different reasons, are not applicable for our problem. One of them would be the big M method. You sort of build a large bounding box around your feasible region. And then for this large bounding box, you know where there is a very central point, and you initialize it. This is a standard thing that you could do. The problem is that how large do you need to choose it? Usually what you could do is, choose it proportional to 2 to the number of bits in your input, but a strongly polynomial model doesn't allow that. You can't do that. That's not possible. Second method, where you do not need large numbers, would be self-dual homogeneous embedding, which is this unpleasant system here. But it turns out that this system automatically can detect primal infeasibility, dual infeasibility. It can automatically give you, in the end, optimal solutions if they exist. However, if you use that, then your matrix structure gets destroyed. So our analysis worked for a system of 2 non-zero entries per column or row. If you do this system here, then what you do is essentially your objective function becomes a constraint, and you end up with inequalities that that are dense. So you can't really apply that. What you can do, of course, is you would think that this system shouldn't change the geometry by your problem too much. So you should think that, okay, I do not have 2 non-zero entries per column or per row anymore, but I mean, the optimal solution of this system is the same as our optimal solution originally. You would think that, I should be able to analyze it, that the straight line complexity shouldn't really change much. And we trialed, but we couldn't figure it out. I mean, there's no negative answer to that. That's an open question. Actually a very interesting open question that when you do self-dual homogeneous embedding, does straight line complexity change by much, by more than a polynomial factor? Okay. So these two approaches fell flat. So what we did in the end was come up with a completely different initialization technique that is very general, applies to general LP, and therefore in particular also for min-cost genflow, that resembles a bit two-stage simplex method. So what do you do in the simplex method? You also have the struggle of, at first you have to find the vertex of your polytope, and then you can run the simplex method to find the optimal solution. So what you do in the first stage of simplex is, write an auxiliary system whose optimal facet are the feasible solution of your original LP. And we do a similar thing, just with more than 2 phases, more like 3 phases. And some phases run in parallel because you have to do it in primal and dual side separately. So we solve essentially 5 interior point methods. So what is the first thing that you do? You solve the conic feasibility problem, which would be find a non-negative vector in the kernel of your matrix with maximum support. That is sort of the first question that you want to do. If you think about min-cost flow, throw away the demands. You only care about a circulation. Throw away the cost. You only care about non-negativity. And the question is now on a direct cycle, on a directed network, for which arcs is it possible that they are positive in any circulation? And this is of course the case for all arcs that are contained in a cycle, which corresponds then to strictly connected components. And so in general, you can do that for all LP. How you do that in LP in interior point method is the following: you add sort of the negative copy of your variable, which would in flow world correspond to you add an arc in the opposite direction, and this you can easily initialize here. Just pick the all 1/2 vector. Then this is perfectly central in a way that you are as far away from any constraint as you could possibly be. And it turns out that the optimal solution to this system is trivial. I can give you one. X is going to be 0, and X bar is going to be 0. That's an optimal solution, clearly. So why am I even doing this? And the reason why I'm doing this is that the interior point method is not going to give me the optimal solution that I just told you. It's not going to give me the all 0 solution, because interior point methods try to stay away from the boundary as much as they can, which means that they will not give me any optimal solution in the end. They will give me the optimal solution that is as far away as possible from the boundary. So in particular, it would not give me the all 0 circulation, but it would send flow around all arcs that are on cycles. Okay? Now, again, for minimum cost flow, it is easy to figure out which arcs are on a cycle. You can do that in linear time. But for general LP, this is a non-trivial problem, highly non-trivial. So there's this. The optimal solution gives you, in our case, I make it simplified. I assume that our graph here is say, every arc is on a cycle. So there is an optimal solution that has positive flow everywhere. And it turns out that you can use now this solution to solve the dual feasibility problem because of the following. You found the solution X star to this system here. And now I just replace my all ones vector with the true objective. Okay? the true objective C that I cared about initially. But the nice thing is that now, with with this solution X star, I already have an initial central solution, which I was not given initially. So the first stage helped me to find the center of the system that I need to solve feasibility. Okay, so this is stage 2. Use the solution from step 1 to solve feasibility. Okay, so maybe that's a bit too much of inequalities here. I don't want to go over it. But it turns out that if you solve the dual feasibility problem, it's not going to give you any dual feasible solution in the end, but it's going to give you the dual feasible solution that is as central as possible, which then corresponds to the so-called analytic center, which is what you can use to initialize the third stage. So if you want to, so here, let me call it Y star, is going to be the analytic center of the dual feasible region, and I use this to solve the actual primal dual problem that I wanted to start to solve from to begin with, and run the interior point method initialized with Y star. Important here is that, unlike in the self-dual homogeneous embedding, I don't add C as a constraint or B as a constraint, again, which are dense, so I can't use my analysis anymore that I spent so much time figuring out. All I'm doing here is I create a negative copy of my variable, so this would still be a flow problem. Here I also do nothing that changes the structure of my problem. I still have the property that I have at most 2 non-zero entries per inequality. And that is why the analysis for Minkowski flow survives this 3-stage approach, which again did not survive the big M method and did not survive self-dual homogeneous embedding. Okay, so those are sort of the ideas about the initialization. Again, this is all generic for LP, and it's not restricted to Minkowski flow. Okay, so far for the theory behind our paper. As usual, there are more new open questions than problems that you solve. The favorite one, the big one in the area, of course, is there a strongly polynomial time algorithm for general LP? As mentioned before, interior point methods will not cut it. There are lower bound examples that are exponential. However, on the way, there are quite a few problems that one may figure out. One of them is Markov decision processes. Can we solve them in strongly polynomial time with interior point methods? It's unclear. We now have an algorithm. We just don't know how to analyze it, how to analyze the SLC for MDP. Then, of course, also speaking in front of a Combop crowd here, is there a combinatorial algorithm for this? Our algorithm is definitely, that's continuous optimization. We definitely use the combinatorics of the problem to analyze its running time, but can we actually find a true combinatorial algorithm? And also with improved running time, because I didn't go over the running time of our algorithm, but it would be in the region of maybe m to the 8 or so, if naively analyzed. So it's very inefficient. You would hope for maybe something cubic or quartic. Okay. Then here, this is sort of a question that is only indirectly related to what I was speaking about today. And that is, all these interior point methods that solve problems exactly, they require at least, in factor n squared, more than interior point methods that only want approximate solutions. For very simple LP, there is also a gap between weakly polynomial and strongly polynomial time algorithms. For example, we can now solve minimum cost flow approximately in almost linear time. However, minimum cost flow in strongly polynomial time is still mn. So there's a gap of factor n. If you think about single source shortest path with negative edge weights, also now linear time approximately. And for 70 years or so, Bellman-Ford was the best to solve it in strongly polynomial time, which is mn as well. And just recently, it was improved to mn to the 8/9, stock best paper award, the last stock. So yeah, the question is, for more general LP, is the gap supposed to be as large as n squared, or is it really more like linear or even less? So yeah, and then maybe this question, which is not the gap between weakly polynomial and strongly polynomial, but more the gap between practice and weakly polynomial, and that is, you need, in theory, root n many iterations to solve, or to get an approximate solution. Why is Siri now active?
I don't know where you are,
Okay.
but you can show me.
Okay. Okay. Where was I? Right. In theory, you still need root n many iterations to solve LP approximately with interior point methods, and it's a big open question whether you can go be lower than root n. However, in practice, you rarely see a growth in iteration count of more than log n. And it is super hard. People tried to even show that for randomized LP, for a randomly generated LP instance, you can get better than maybe root n iterations. It's very hard to analyze. So yeah, that as a maybe last open question here. And yeah, I guess that's it. Thank you.
Yeah, if there's any questions, please let me bring the mic to you so your question is recorded.
I have two questions. So for your initialization thing, I guess so you had mentioned that for the primal feasibility, there was strongly polynomial time algorithm, but that kind of solution would not work because maybe it gives a vertex solution? Or?
Exactly.
Okay.
Yeah.
Right. And the second question, so I guess one way of looking at what you're doing is that you're able to solve this LP with two variables, but then you can handle a third constraint, like if I think of C transpose X less than equal to B as a constraint, right? You can do that because you can optimize C transpose X over the remaining constraints. So have you thought about, like, if there are, let's say, a constant number of general constraints or constraints with three variables, like would things extend?
We thought about that, but it seems to be highly non-trivial how the running time will change. Yeah, so we have, no, it seems to be hard. Yeah, but I agree. I agree that the answer should be something like, 2 to the number of constraints should be the increase in running time, but no, we couldn't figure it out. And maybe to add to your first question, actually, we can use primal feasibility to initialize. However, you would need to write order n many systems to sort of, what you do is you solve primal feasibility, and at each time you maximize one of the coordinates. And you can do that n times, and then you can initialize by using a convex combination of the solutions. Done. But it's far less elegant. Yeah.
So thanks for the very nice talk. Let's see. So this is just a small thing. In your min-cost generalized flow, did you require the costs to be non-negative?
Oh, no, absolutely not.
They were in the denominator, though, at some point in your talk. There were costs in the denominator.
There were costs in the denominator? There shouldn't be.
Oh, there shouldn't be? Okay.
No. I mean, in the end, what you do is you implicitly solve dual feasibility anyway.
Okay.
And you take any dual feasible solution which is non-negative.
Okay, great. Okay, thanks. And then with regard to your open questions, you asked a very general question about universal exact methods for more general convex problems. But you could ask a more specific question, which is there a generalization of SLC beyond linear programming? So I suppose you probably thought about that question.
Yeah, so what you can do is, I think, even going to quadratic objectives, you can get it that your max central path curve is root x, and root x has infinite SLC. So there you're done. But you can generalize it to sort of, combine a couple of splines of higher degrees. So there are notions that make sense, but it's definitely interesting to figure out. The problem is once you go to SDP, then you cannot do it exactly anymore because your representation, it's just, you cannot do it in a certain number of bits and in a certain space as a function of your input space. That is why this is the feasible, possible generalization of what we're doing, just going to quadratic problems, convex quadratic problems. Yeah. Yeah.
Are there any other questions? Right then, let's thank Bento again.